Hello, everyone, again, and welcome to the first session of our fall program for VISIM. Today, we have the pleasure of having presentations from Meet Saiya and Max Ng. Each presentation should be about 20 minutes long, and then we'll have time after each for Q&A and any comments or audience participation. So you can just, chime in at that point or put it in the chat if you can't speak. And then I'd also like to point out that the meeting is being recorded, and we'll be uploading a recording of this later on our YouTube channel. So with that, I'd like to introduce our first speaker. Meet completed his MTech from the Indian Institute of Technology, Kanpur, specializing in infrastructure engineering and management with institute recognition for academic excellence. His thesis focused on incorporating economies of scale and pavement and asset management framework. And during his internship at the Bureau of Indian Standards at GOL, he examined various ISO, ASTM, and Eurocode standards along with the latest literature to make recommendations and help improve over 30 indigenous BIS standards to incorporate sustainability into codal provisions. Currently, he is working at AECOM, in the Capability Center as a junior bridge engineer in the rail structure team. So with that, I'd like to hand it over to Meet, and thank you again for presenting.
Yeah, thank you, Adrian, for that nice introduction. I'll share my slides in a moment. Go to slideshow. I hope my screen is visible.
Yes.
Yeah, great. So let's get started. So I'll be presenting today my thesis work. My mentor Aditya sir is over here. I'll be presenting. So the topic is incorporating economies of scale in a top-down payment management system. Little bit of introduction. So maintenance, repair, and rehabilitation basically means that we set up an optimization problem, either to sort of minimize cost subject to quality constraints, or we can maximize quality subject to budget constraints. Basically, what we want is best condition of asset per buck spent. And there are some features in the decision-making process. First is asset condition states. So we ought to have some condition states where which we can measure how good or bad the asset is. Then we have action space, wherein it's a possible maintenance action that we can do. It can be like from do nothing to reconstruction, so the spectrum of maintenance actions. Then we should have performance models which would sort of decide, given an action that we do, how would a state transition to another state, or how would our asset transition from one state to another state. And we should obviously have agency costs that the agency would incur for doing some actions. And then we should have user consideration. So we can have user consideration in two ways. We could have serviceability constraints, or we could have costs directly. So there are broadly two kinds of approach: top down and bottom up. So top down approach basically means that we aggregate the infrastructure at network level and then sort of come up with policies. This is mostly applicable for kind of infrastructure that are homogenizable. So pavements, maybe pipelines, transmission lines, something like that. Typically so for payment we usually have Markov decision processes, wherein which basically means that the future states are just a function of current state, and probability deterioration period. So in this study we use probability deterioration function, and these are popular in this kind of setup. Bottom-up approaches typically are used for kind of infrastructures like bridges, tunnels, which sort of an individual identity, and you want to model that. So each of them is different from another, and you want to integrate that in the modeling framework. So it allows for continuous state, continuous action spaces, and so and so. So this study typically focuses on top-down payment management models in stochastic framework. Right. So first implementation of such a model was by Gulabi Kulkarni and way back in 1982, and they saved a third of the budget, agency budget. they proposed two kinds of formulation. One was steady state and transient state. So steady state formulation basically is distribution that doesn't change over time. So basically, suppose you have state A, state B. B is the worst state, and then you do say 20% action on B, it moves to state A, and state A naturally deteriorates and 20% state A deteriorates and come back to B. So you again next year have same distribution, and again next year you do the same action. So this kind of distribution is basically helpful because it helps plan for budget and remove sort of variability from the system. So it's easier for it's easier to implement. So that's the goal state. And transient state is something that your current distribution might not be the best steady distribution that you have. So how do you find the cheapest path to go from transient to steady? Right, there have been several extensions to these models incorporating various different things, but the basic premise has been same. So you want to minimize the cost subject to some quality constraints, and so there are steady and transient models, right? These are the set of notations used in the model. So S is the set of condition state, A for action, T for timer, N for number of asset, for U gamma for discount factor, and uh, this is probability transition matrix. So I'll show it over here. The Let me turn on the user pointer. Yeah. So these are our decision states, which are fraction of states in state one, on which we are going to do action one for time period t. So WS4A3 would mean that we are in state 4 and we are going to do action A3, right? The fraction of such states. And transition probability matrix is basically a matrix that would say how that states would transition in, like how the states would evolve given an action. So for example, here if we do nothing and if we are in state 1, 40% chance we'll go in state 2, 30% chance we'll go to state 3, so on and so forth. uh, so this is the linear model. We have ASA, which is the cost, unit cost, times the fraction and times the total number of assets that we have. So fractions time n will give the asset in state S on which we are going to do action A, multiplied by unit cost, and we sum over all states and all actions. So this is minimize agency cost. And here we have some constraints. Sum of all states would be 1. This is state conservation or state transition, which means if you are in state S-A and you transition by transition probability matrices, you should reach a new distribution WSA. Now, since this is steady, WS-A and WSA are the same. So which means that you are in same distribution, you transition and you again reach the same distribution. And this is the serviceability constraint that you have, that the we want to limit the worst fraction below a certain threshold. So that is the kind of serviceability constraint that we have. And we have non-negativity constraint. So this is the basic steady model. And here unit costs in the objective. So here we have unit costs. Similarly, we have transient model wherein we just have a WSAT instead of WSA, and we discount over some and then some sum it over all years. So we have minimized discounted sum of cost. Again, sum of all state action should be equal to 1. We should transition here, and then we should reach to t plus 1. So like if you are in WSAT, you transition by transition probability and you reach a WSAT. And again, some serviceability constraints and some of all. So here you also have initializations of state. So for example, at t is equal to 0, you want to have certain distributions, you assign it to them, and then you have non-negativity constraints. So this is a transient model, typical transient model. Now we come to brief overview of economies of scale. So it basically refers to the marginal savings in cost if you do same kind of maintenance activity, more and more of same kind of maintenance activity. And we have some evidences. So for example, Worm and von Harten, they note that there are some savings if we do that. Moen and Sperrell, they did some regression in on the data of maintenance data in Chile. Similarly, Gracia and Sen did some study in Switzerland, and Philweed did some study in UK. So they all found that there is some evidence to in economies of scale. And we proved here the cost functions generally that include economies of scale should be concave in nature. So generally, for some economies of scale to exist, the unit cost multiplied the times the activity is going to be done should be greater than equal to activity done at scale, right? So it's done cx times over here. And the way we prove that is we just assume that if you do nothing, it's going to cost nothing. So f0 is 0. And here concave function, this is a definition of concave function with just y equal to 0. So alpha x plus 1 minus alpha, this is going to be this. And we simply remove these two terms because f0 is 0. So we get f of alpha x is greater than alpha fx. Right now we've used this independently on 2 points a and b. So here fa plus fb, we just multiply, divide this by a and b. And we use this property individually on this and this, right? So we get this. We just bring this out and introduce, instead of equality, we introduce a inequality over here. And as we can see, this is going to be fa plus b. So we have fa plus fb is greater than equal to fa plus b. And if you replace a by b, you get f2fa is greater than equal to f2a. And if you sort of do this recursively for k times, you get this thing, kfa is greater than equal to fk, which is what it's written over here, which basically means that functions that incorporate economies of scale have to be concave in nature. Yeah, so we then look at literature to look up what are the kinds of functions that have been used to model economies of scale, and we come across this formulation, which is log cost versus log lane miles maintained. We just take an exponential of this and we find this. Similarly, for Moen and Sperrel formalized is modeled as this. These two, so this is total price, this is unit price, and both of them have similar function, right? So we hypothesize that total cost is going to be of this nature: E P plus Q log our P is away, right? So that would mean that this is unit price, and B is intensity parameter. So one, it becomes unit cost. At 0, this goes away, and this becomes unit price again. So it's sort of subscription model, if you will. And if you divide total cost by NW, which is the number of roads on which you do certain maintenance, you get b minus 1. And then if we retrace the steps back, we can see that this is this formulation. So the only difference between this and this formulation would be
Meet, your video is hanging up a little bit. Maybe you can turn off your
right, it will be minus 1 in the unit price. So we so yeah, let me know if it's better or not. So we just use this cost function to account for economies of scale in the same two formulation we showed earlier. So the only thing that changes in steady model is this b that comes over top. The rest, all of it remains same, because the quality that we account for is going to be the same. It's just that how we account for cost changes. So that's why the objective function changes, and we have this b over here. Now this b is between 0 and 1. So this is w to the power some fraction, which will mean it's some root of some root of kind of functions are going to be concave. Similarly, for transient model, again, we just
your audio is crashing a little bit.
This thing. And the features of the model, it's a concave objective function with linear constraints. So broadly, this is a non-convex problem. And if you, so generally, it is an concave operation problem. It's of I don't really know.
That's okay. I mean, just power
is
on.
it all right now?
I mean, just
Hello?
keep going on. I can't really
Yeah.
go ahead.
Sorry, I think my Wi-Fi is all right, but I
Yeah, that's
really
okay.
don't know.
Just carry on.
Okay, sure. So this is a non-convex optimization problem, and we propose two solution methods. One is linear approximation and piecewise linear approximation, and another is sigmoidal programming. So I'll briefly touch upon both of them. So this is an illustrative example. So for I'll explain the methods with an example. So here we have some function minimize root x root y, which is this grid over top, and the bottom colored plane that we see is just x plus y plane, right? So for reference, and we have subject to these two constraints. These two constraints are basically represented by these lines, right? So here I want to like sort of highlight what the change is going to be. So the optimal solution of x plus root y is going to be at 0 1 or 1 0, which is going to be 1. But if we just assume the linear part of it, x plus y, we can see that this is going to be 0.4 over here, right? The value is going to be 0.8. But if to account for economies of scale and substitute this, we can see that not only the solution changes from 0.4 to something else, but also the objective value changes. So in terms of our problem, the maintenance action are also going to change, and the total cost of that is also going to change. And we do so I'll solve this by piecewise linear here to demonstrate how we do it. So for example, here I have given broken this root x and root y in two lines. Uh, Here these two lines, and then I say minimum of this line, minimum of these two lines is going to be an approximate for root x, and minimum of these two lines is going to be an approximate for root y. So here dx and dy are going to be minimum of these two, and then instead of the entire root x or root y, I use this surrogate dx and dy. And so here sort of I've shown that if you solve in Cplex, you get a solution 1, and we have two optimal solutions. For sigmoidal programming, the first thing we do is we draw the tightest concave, which is this straight line over here. Solution is going to be 0.4. And then we do branch and bound over here. So here, for example, this is the error between the approximation and the original function, and similarly this is the error. Now in this case the error is the same, so we can snap any of it, but in case the error is not same, we snap the maximum difference. And now we have two lines, which is this line and this line. So these two becomes the right branch and left branch for the next problem. So instead of x, I just substitute this line, and instead of x over here, I substitute this line, right? And then we have same problem, but just now we have diff branch. So x is going to be restrained. We see that this becomes a problem, and here the optimal solution is over here, right? So it's 0 1. And the way we stop the algorithm is basically we check for f at minus f. If it turns out to be 0, it's optimal. So here we can see that if we put x equal to 0 and y equal to 1, it's going to be 1. And so the approximate is going to be 1, and the x to power 0.4 plus y to power 0.4, that is also going to be 1. So now we know the solution is optimal. Similarly here, if we do that, we find the solution is over here. And if we again check f at minus f, which is 0.612 plus 0.387, it is going to be 1 again. So this is also optimal. So this is how we solve the problem. And then so this branch and bound continuously find the solution, and we implement this on a synthetic data. So this is a synthetic data. We assume 5 states, 4 actions, 20, so 0.9 discount factor, just n is equal to 20, some costs, and few transition probability matrices. And then so this is basically what happens is that uh, for piecewise linear, the computation time increases exponentially. So this is log normal curve or of number of breakpoints and computation time, and this is the objective function. So objective function usually decreases, but sometimes can increase decrease. So based on the computational limitation, we chose that n equal to be n should be equal to 10. So number of breakpoints over 10, and then we implemented the synthetic example. So these are the results. So basically this is improvement of incorporating economies of scale into
We've lost you again.
we save some additional money. This is for steady state, and this is some savings. But as and when the becomes boxier, so to speak, and n equal to 10 is not a good enough approximation. So, uh, uh,
I
or
think it's catching up.
hello,
It's one of those things. I think
hello.
you lose it, we lose your voice, and then it all kind of comes together. So maybe keep talking, and
Okay.
we'll hear you at some point in time.
Yeah. Okay,
Yeah. Carry on,
sorry,
carry on.
sorry for that. Okay, yeah. So as I was saying, we see some additional savings in if we incorporate piecewise linear, and for sigmoidal, the termination criteria is that if we either have 0.1% optimality gap or 30K iterations, and typically we hit max number of iterations with some optimality gap. All of these computations are done on i7, 6, and 8 GB RAM, and so yeah, this is the optimality gap that we usually see, right? And so for example, this is a real range of economies of scale that we observed from the paper. So here the optimality gap is roughly around 5% to 15%, but there is some significant optimality gap, and this is the improvement over so savings in cost in over linear model. So for example 0.85 to 0.65, we can see around 20%, so somewhere around 5% to 20% in steady state, and somewhere around 2-3% to 8-10% in transient state. So conclusions, yeah, accounting for economies of scale, the problems actually becomes hard, so because it's non-convex optimization problem, but it's worth solving because we see some additional benefits in terms of cost, and piecewise linear offers a quick solution, but since we are solving an approximate problem, there is no guarantee in terms of optimality to the original problem. Sigmoidal programming is computationally very difficult to solve, but we get some estimates on optimality gap, and so results on synthetic data demonstrate that state action distribution change as well as the maintenance costs come down. Yeah, thank you.
Thank you. At this point, any questions from the audience?
I have a couple of questions. Like first, this is pretty nice. I think that I really liked your work. So in terms of the
Thank you.
formulation, the two questions that I have are this. I think that in your model, you just have the objective to minimize agency costs subject to not having more than a given percentage in essentially bad condition states. So in other words, there were no, let's call them operation or user costs in the model, but just agency costs. And so this is just a clarification question.
Yeah, so there's
Okay.
no agent, so there's agency cost, and in terms of serviceability, I want to limit the worst fraction.
Okay, so just agency cost, not user cost.
Did I answer that?
Yes. No
The
user
thing is,
cost.
I
No,
lost
no,
you
no,
for a
not
No,
user
second.
no
cost.
user cost. No user
Okay,
cost is
so that was just
serviceability criteria.
that was just
Yeah.
a clarification.
Yeah.
And then basically related to the policy, once you consider these functions that are I guess concave, essentially, so what is happening to the policy? And so intuitively, one, and I'm not sure if you showed this in one of the slides, but like intuitively, what one would expect is that you would have just a little more preventive maintenance, meaning that
Yeah. So in the interest of time, I did not show you, but I think I have that as well. Uh, so for example, this is one of the transient state for let's show for sigmoid, both are same, but this is a bit nicer. So here so this is a snapshot from year 2 to year 5, And this is the economies of scale are going from say 1 to 0.2. So increasing economies of scale from left to right. And if you see from year 2 to year 5, so we okay, yeah, here's my pointer. Yeah, so we can see that, so these are actions. So we can see a lot of red here, that is reconstruction. And as we go, as we improve, like there are more economies of scale, maintenance is preferred. So that is one thing that we see over here. We also see sometimes that the system is maintained at a higher level. So for example, dotted line is the uh, threshold that we want, but sometimes system is being maintained at a higher level, and then it lets naturally deteriorate. Till then it does a lot of reconstruction over here, and then again the best state increases. So this kind of cyclic action is also captured in the framework. Does that answer your
Yes,
question?
yes. I think this is great. I think that this is I need to look at it more carefully, but overall, I think that this policy can be quite insightful.
Yeah. In the interest of, I mean, I did not show it.
It's perfect. Thank you. Yeah, and
Thank
so
you.
the only last comment that I will make is I think that when you have concave costs, what you have is essentially decreasing marginal costs. And so I just wanted to make you aware that this is subtly different than economies of scale. And so there are counter examples where basically essentially economies of scale, there is like an axiom in economics that economies of scale do not drive decisions, but rather it's a marginal cost. And so I don't know if you published this paper, but it's just something to be aware of. I'm not sure if it makes a difference in this analysis, but occasionally there are counter examples out there.
Okay. I'll look into it. Yeah, sure.
Yeah.
So what you mean to say is that marginal cost affect more than actual cost.
This is what drives decisions. And so,
okay.
and I can send you a counter example, like basically where economies of scale do not lead to these expected changes, but rather, I mean, it's the differences in marginal costs. And I think that in your case you used concave costs, which basically are both. The condition, in other words, the condition of a non-increasing marginal costs, a concave utility function, concave cost function, is a little bit stronger. And so that's what I wanted to make you aware of. But this is a technical point. I think that it takes nothing away from what you did.
Okay. Yeah, I'll show it, but I'll look into it.
Yeah.
It would be great if you could send me the counter example as well. Yeah. Thank you.
Thanks, Pablo.
Thank you. Any other questions? Okay, so then thank you again, Meet. And if that's all good, then I'd like to introduce our next speaker today. So Max Ng is a PhD candidate in transportation engineering at Northwestern University, and his research interests lie in public transit, smart mobility, network modeling, and data analytics. He's currently collaborating with Argonne National Labs on the project redesigning multimodal transit systems with shared fleet mobility services, which he will be presenting some of his work on today. He has previous experience in rail decarbonization and freight resilience, and before joining Northwestern, Max obtained his bachelor's degree in civil engineering at the University of Hong Kong and worked at the MTR Corporation. He's a chartered civil engineer in the UK and the Institution of Civil Engineers representative for the USA Midwest. So with that, I'd like to hand it over to Max.
Yeah, thank you. I was finding the unmute button.
Yeah.
Thank you very much, Adrian. And today I'm very happy to be able to share with you our research at the Northwestern University Transportation Center on the transit network redesign with shared autonomous mobility services. As Adrian mentioned, this is in collaboration with Argonne National Lab, who is also based in the US. And these are some of our co-authors, Professor Hani Mamasani, Dr. Oman Ferbes, and Dr. Tana Kuyasa of the Argonne National Lab. and also Roman Engelhardt from the Technical University of Munich. So the motivation of our research is that we have seen quite a lot of declining transit ridership in the US or in North America, particularly after the COVID-19 pandemic. Some researchers or some public have seen shared autonomous vehicles as a solution to the transit network or transit services, but also many researchers have pointed out that if we have very convenient point-to-point services of the SAVs, we will see more traffic and more demand on the road. So our goal of the project is to redesign a multimodal transit network with SAMs, shared autonomous vehicles. So we want to develop an optimization framework to redesign transit network and offer a scalable solution to consider these SAVs with the existing transit modes. We also want our tools to be able to be integrated with other simulation tools such as NUChance from Northwestern or Polaris or VISIM. So let's look into the problems that we are trying to solve. We want to minimize the total generalized door-to-door cost of a transit journey. That is to say, we include user and operator costs. For example, when we want to go from an origin to a destination, then a user, they may have to walk or take a feeder to the closest transit lines, and then they have to wait, and then they ride on the transit lines, and then maybe they will transfer from mode to mode, such as from a bus to rail, and they wait again, and they ride on that. And when they reach the final transit stops, they would have to walk or take another feeder to their final destinations. And these are all the costs that we have to consider when we try to model the whole transit network. So this is actually kind of a classical transit network design problem, which has been proven NP-hard nearly 40 years ago. We also seen nonlinearity because when we consider both the path level riding cost and also link levels such as infrastructure investment, whether we want to build a rail from zone I to zone J. And the costs are also non-convex in general. And when we consider multimodal at the same time, there will be some interactions like competition between different modes. For example, if we are developing a new bus rapid transit BRT link, then maybe they will draw away some of the ridership from the existing rail that will harm the economy of density at the same time. So the contributions of our study is we developed a multimodal transit network model by characterizing the geospatial demand and also the performance of each mode with clustering and continuous approximation. Then with this input, we formulate the transit network design problem with a minimum cost multi-commodity network flow problem. So we can solve it with an MILP, mixed integer linear programming solver. And where specifically, we are trying to label each flow variables with their origins. And at last, we also expand this MCNF for route generation, but probably we wouldn't have time to discuss that today. So the solution is broken down into 3 steps. The first, we want to cluster our study area into 50 or 80 zones. So then in each zone, we can compute the cost and the modal performance, for example, distance to travel in that zone and the time. Then with this input, we have the zonal connection optimization as an NILP problem. So I have to determine the system optimal link connection. So from zone A to B, which mode we want to connect them. Are we using rail or using BRT, for example? And then the system optimal flow assignment. Then the next step is from the zonal connectivity result, we do the route generation. And we use the routes as the transit network design to fit into a previous work also from Northwestern that we try to optimize the transit frequency and the SAV fleet size with the use of agent-based simulation and also considering mode choice, path choice, and SAV simulation. So let's look into the mathematics of the model. So the first step is clustering, and we use k-means clustering weighted on the number of trips in each zone. So that means if the zone has higher density or higher number of trips, they will be assigned smaller clusters. For example, you can see this small zone here is the Chicago loop, which is the CBD here. So they are assigned a smaller zones to represent their significance in the whole network. And also we have to consider the network connectivity, because just 50 zones, if we consider all the OD pair within these 50 zones, there will be a lot of a huge solution space. And therefore, we limit that by only considering certain number of OD pairs. For example, each zone is allowed to connect to the adjacent zones, to connect to the highest OD dimensions, or if they have an existing rail connection in the current network. So I want to show you how the existing network are captured in our network model. So on the left-hand side is the commuter rail GIS, which is called Metra. So you can see the colorful lines are the actual rail track that we're using. And in the model, we are using 50 clusters. So you can see we connect zone from zone, but there is some loss of details. But basically, we try to capture as much as possible whether two zones are reachable by a certain mode. And with the clusters, we can compute the cost in each zone based on continuous approximation. So I wouldn't go too deep into details here, but basically we are assuming a uniform distribution of demand in each zone. So for example, if you want to know about the feeder distance, like how much on average a traveler would take the feeder, how long will it take to go to the transit line, then we will assume the passengers to be around at the half distance to go to the main route. So the distance, the feeder distance to travel would be around quarter length of the zone. And with this, we can also estimate how many people would use feeder over walking, and also how much cost will it take to operate those feeder. Then next, we are representing the whole multimodal network with an interzonal digraph. So you can see here, we are showing two zones, and each zone is composed of the central node and also the modal node, which are blue around the central node. There are 4 types of arcs here, from central node to the modal node. The green arc is the starting one, that is to represent the traveler starting their trip, then they go to take, for example, BRT. And the opposite direction from a modal node to a central node is the red arc, the ending arc. Then from zone to zone, then they can travel on the same mode. For example, if there is a rail service, then they can go from zone I to zone J with rail. Then the blue arc is an interzonal travel. And the last one within a zone, they can also do an intermodal transfer. That is to say, they transfer from SAV to an express bus within zone I. Then with these 4 types of arcs, we can use the previous zonal continuous approximation results to estimate the cost of each arc. For example, for equation 7 starting cost, we consider the walking cost for those passengers or travelers who don't take feeders. And then if they take feeders, then it will be the second term. There will be waiting cost for the feeders and also the traveling time on the feeder. And then the last term would be the waiting cost for the main line. So all these 3 costs combined would be the starting cost, for example, taking rail. And then the next equation ending cost will be the opposite, except it would be similar, except that we don't have to include waiting cost here. Then equation 9 is the intermodal transfer cost that we assume, for example, if you change from a train to a bus, you may have to walk to the bus stop. So there's a transfer penalty here. And you also have to wait for the bus headway. Then equation 10 and 11 is the interzonal riding cost that is traveling from zone I to zone J. If you're on a mode M, how long will it take for you to go from there? By considering the through distance within both zone I and zone J, and also the clear distance. For example, there is a highway from zone I to zone J, then that capture all the distances you have to travel. So when we have the arc cost, then that gives us the all the information we need to do the multi-commodity network for problem to optimize the zonal connection. So you can see equation 12 is the objective function here, where we are summing up over all origin pair and all mode. We have 6 different groups of decision variables, and the first 4 groups are the flow variables, and we are labeling them by origins only and not by OD, because if we do it by OD, then we will have too many variables that our solvers can handle. but it's also sufficient that we only label them by origins that I will explain later. But basically, the flow variables are the 4 archetypes I've mentioned. And also, we have 2 groups of integer variables that they govern the zonal connection and zonal infrastructure. That is to say how many number of links we want to build or we want to use from zone I to zone J. That's the lambda and omega here. And these 6 types of variables are built into the objective function. So for the first row of the objective, they are all users cost from starting, interzonal trip, transfer, and ending. And they are simply the arc cost multiplied by the flow of the corresponding arcs. And then the second row is the operational cost, separated into the main line, main transit line, and also the feeder services. For these 2, we have to estimate the number of vehicles or number of trains required based on the arc flow. And we are using design occupancy here, which is the denominator. And for feeder, we also have to consider some travelers, they are using feeders and some of them are not. So we have the eta as a factor to account for that. So for the constraints, as this is a network flow problem, so there are a lot of flow balance constraints. For the first 2 here, we are to ensure that the demand is satisfied. As I mentioned, because we are labeling the flow variables by origins, so at origins, the sum of all starting flow variables would be equal to the sum of all OD demand for that origin. And then on the right-hand side is the ending arc. So for some of the ending arc flows would be exactly that OD demand because we are labeling all flow variables by the origin. Then for flow balance constraint at the modal node, for example, this one here, it's quite simple because after we label the flow by origin, we can ensure that there is no inflows from other nodes. And there will also be no intermodal transfer and no terminating flows at the origin. And therefore, the starting flow will be equal to all the outbound flow summed up together, which are the orange arc here. And then for non-origin flow balance constraint is a bit more complicated. We only know that there will be no starting flows outside origin. So we need to include all the flows, such as the inbound flows, which are the blue arc from other zones, and the opposite direction outbound flow to other zones, the orange arc. Then there may be intermodal transfer, such as inbound, the purple arc from other mode, and the green arc outbound to another mode. And also there may be ending flow, which are terminating at this zone. And everything for each mode, each zone, we have to satisfy the flow balance constraints. Then the next 4 constraints are about the zonal connectivity and infrastructure. The first one has to make sure that we are building the new links within the infrastructure budget. And we are using a distance-based estimation here we have a different unit infrastructure cost for different mode. Then equation 23 is to make sure that we are building sufficient links that are required by the model. So we consider the requirement, which is lambda, and also the new links that we are going to build, the omega one, and also existing links in the current network. Then for equation 24 is to match the zonal connectivity variable with X superscript lambda to the arc flow F superscript lambda. We consider the hourly capacity provided by each link. So this is the coefficient here. The numerator is the maximum occupancy of each vehicle, and the denominator is the minimum head weight. So this is to say the hourly capacity of a link. Then in the end, equation 25, we have to make sure that we build the link from zone I to zone J. Zone J to zone I will also be available for usage. Then the last 4 constraints are mostly on the shared autonomous vehicles. We are trying to put a cap on the arc, the origin, and also destination. And also we use a free size to govern the whole net, how many people we can serve within the whole network. So with this formulation, let's look into how they would behave. We make use of an example in the Chicago metropolitan area. So we cluster the whole area into 50 zones. And we have 3 scenarios. The first one is an existing rail infrastructure. We use the existing metro and metro rail network with no new infrastructure investment. Then the second scenario is similar, except that we give a nominal infrastructure investment, which is $15 billion, a similar amount as what Chicago has been spending on infrastructure on transit every year. Then scenario 3 is a greenfield design, which means we have no existing infrastructure, but we have a lot of money to build a similar scale of the current rail network. So scenario 3 is a totally hypothetical scenario. Then next, we are using the demand data from the Chicago Planning Agency, and we consider 5 different transit modes, both commuter rail, metro rail, BRT, and for buses, we have 2 different classes, which are express and local. And also, we consider the point-to-point SAV as a competing mode as well. Then these are the computational results of the 3 scenarios. So there are around 1 million flow variables and also 20,000 individual variables before we use Gurobi, so this is the before the PSOLVE number. And then the computation time for scenario 1 is basically just a flow assignment problem, so it usually solved within a few seconds. But for scenario 2 and 3, we assign 23 and 46 hours, and we achieve around 1.5% solution gap within that number. So it's pretty fast, I would say. And as you can see, the 3 scenarios going down, we're actually relaxing more and more constraints, more and more freedom to do transit redesign. So of course, the objective and generalized cost would be lower and lower, and so are the generate time. Yes. Now look into the designed network. So for scenario 1, we are only using the existing rail network, but we can redesign the bus network between zone to zones and also the SAV. So you can see SAV capture around 14% market share by trip count and around 15% market share by the distance traveled. And we have some express buses which are around 5 to 8%. But if we go to scenario 2, where we can spend some of the money on new infrastructure, then you can see on the metro side here, there is a new link. We usually call it O'Hare Express. So that's providing a faster service for people going from downtown to O'Hare Airport in Chicago. And we also built some BRT services, mostly in the suburban areas, and less express buses, because they can see the market share more goes to BRT. And also the SAV market share also dropped, mostly shared by the BRT as well. Then for the last scenario with greenfield design, it's actually quite interesting that we can see we no longer have any commuter rail, but only metro rail. The service area go further from the city to some closer suburban areas, but the further suburban areas are all served by the BRT. And we have very, very limited SAVs here. So I would say SAVs are actually quite helpful in a transit network when we do not have the freedom to spend a lot of money to do redesign or to put new links. But if we can really do that, actually, we want to use the economy of density of transit because we are all doing a system optimal design here. So to conclude, we have proposed an efficient approach to transit network design and also route generation. We see SAVs, there are some helpful roles to play in a transit network, even if we are only considering a system optimum. And the zonal connection optimization formulation we showed here are actually quite efficient and helpful to deal with a large-scale city-sized transit network. So I didn't have a chance to present the route generation algorithms here, but if you are interested, you can also take a look in our paper. A preprint now we have uploaded to archive. So thank you very much for your attention. I would love to hear your feedback and comments and answer any questions. Thank you.
Thank you, Max. Very interesting. Any questions from the audience? Yes, Aditya, please.
Nice presentation, Max.
a lot of detail and trying to combine the network design and other aspects for multiple mode types. One question that I had was, given that the clustering aspect of this formulation it's a standalone element. I mean, I'm guessing, I could have misinterpreted it, but it looked like the zones were defined from the clustering and then they were taken as is to carry out everything else.
Yes.
So given that, at the end of the day, the network exists for everything, right? It exists for within a cluster, outside of a cluster, interzones, everything. So how sensitive is the design to the cluster representation? For instance, we had not weighted it, if they were too broad, if they were too small, how would they influence the design? And
Yeah.
having said that, then is there a certain or is there a certain dimension that you desire from the clusters so as to inform robust planning?
Yeah, that's a great question. Thank you very much. Clustering is quite an important part in the research. And actually, I have tried out different number of clusters. At first, I started with 30 because it's faster. And I realized when the cluster is too small, because we are only considering interzonal trips here. So if the cluster is too small, we have to ignore all the trips inside that zone. And therefore, it may not be good because I think for 30 cluster, we are ignoring nearly half of the trips, as a lot of trips usually don't travel that far distance. And for 50 clusters, we start to see a more representative network that we have more trips that go from, that measures the computing patterns that go from, at least from the northern side of the city to southern side, etc. And I would say, of course, more clusters are better, but there are also the computational costs here. For the case of Chicago metropolitan area, I would say around 80 clusters would be the sweet spot that we can both capture most of the trip, while the computational time is still reasonable, usually within a week. Yeah, I hope I have answered your question.
Yeah, man. Thanks, Max. I look forward to reading the papers as well. Thank you.
Thanks.
A quick question, Max. And so it seems that one of your contributions is to add essentially the dimension of shared autonomous vehicles into the network planning. A question that I have is, you did show us some differences in the networks. I think that I missed a little bit your discussion on what role are these shared autonomous vehicles playing? Are they basically becoming transit feeders? Are they doing essentially point-to-point trips? I missed that a little bit. I don't know if you can provide us with some insights.
Yeah, good questions. I didn't cover that detailed enough. So SAVs in the whole network model that we consider have two roles. The first one is a point-to-point SAV that is a direct competition against other transit modes. So you would just hop on a SAV and then they bring you to your final destination that bypass the whole transit network. But then the second one would be a more collaborative road with transit that they are feeding all the passengers to the transit modes, which we think is more important, especially in the American context, because a lot of people living in suburban areas, they are quite far from the transit coverage. And if the transit agency have to provide a feeder service to all of them using the current human-driven vehicles, then they either have to do a very inconvenient fixed route buses or very expensive demand-responsive transit. So we see shared autonomous vehicles have the role to play here. They offer lower cost, but much more flexible service. And that's make the whole model feasible because a big assumption in the model is that the people will either walk or take a feeder to a transit line. And it is not very likely in the current case, but most people will just drive in that case.
So a follow-up on that, in the examples, the numerical examples that you showed, the mode share that you show as SAV, in some of those, this is the feeder SAV or
interzonal. So that would be the point-to-point SAV.
Okay.
Yeah. So, I'm sorry, that's maybe misleading, because like, for example, when I say we don't need SAV for scenario 3, but that only means the interzonal or point-to-point. So for feeder SAV, we actually still use them a lot here.
I see. Okay.
Yeah.
And is that something that the model is also a decision variable in the model, and so you're able to report statistics on that usage?
Yes, although that is like a predetermined portions by the continuous approximation. So we assume, or we approximate how many people are using SAV feeder based on their distribution in a zone. So if they live close enough to a transit line, they would just walk to the transit lines. Otherwise, they would take feeders.
Yeah. Okay. Any additional questions?
Thank you, Thank you, Max. Thanks to all for attending. I don't remember what is the date for our next session, Adrian.
It should be October 6th. Yep.
Yeah,
And
so we look forward to having you all.
Yeah.
And thanks for continuing with this initiative. I think it's a wonderful concept.
Yeah. It's amazing. I think I'm pretty sure this was our first presentation from India. And so it's amazing. I think that if we didn't do it like this, I think that it'd be impossible to hear what work people are doing.
Yeah, absolutely. Thank you again. And thank you, Max. And thank you everybody for joining today, and stay tuned for the following ones.
Yeah, thank you.
Thank you.
Thank you very much.
Bye.
Take care.